Hey guys, so in this video I want to talk a little bit about mechanical waves. And right here I've got a rope, and we're going to be considering a particle right here on this rope. And you can think of this, maybe it's just one atom on the rope of, if this rope was, say, like a copper wire, one copper atom on this wire. Could be a rope wire, anything. All we need is just something that can be waved up and down, like so. This. So if you wave it up or down, it will make this kind of wave shape. You can think about that, if you take any kind of, like a jump rope and attach it on one side and start waving it up and down, you're going to see this kind of pattern. Even if you don't attach it, just have it on the ground, start going up and down with it, and you will see it makes this kind of wave pattern. We're going to be looking at that. That's called a transverse wave. And we're really only going to be looking at a transverse wave in this video because we are not really focused on the mechanical, qualitative concept of a wave. I'm just explaining this to you so you understand what this equation means, why this equation makes sense. But we're really just going to pay attention to this equation. We can generalize this in quantum mechanics, and we're going to be dealing with it a lot. Okay, so this particle, at any given point in time, say this is one snapshot in time, it has a displacement, right? The particle is going to be up here, so its displacement is the length of this line. And you can have a particle, over here, whose displacement would be there, particle over here whose displacement is down there, and that's negative displacement, right? Because displacement can be thought of, think of it as a vector, right? So it can either be positive or negative. It has a direction associated with it. It's either displacement up or displacement down, right? And what we've got here are graphs of the displacement here. So this this x graph, right, is going to sort of be a snapshot like this at any given point in time, because you can see based on the equilibrium position, that's going to be the position horizontally on this line, right? This particle's displacement is different than this particle's displacement, which is different than this particle's displacement because of its equilibrium position. So we can write an equation for, based on x, based on equilibrium position, how displaced the particle will be. Additionally, you can imagine if this gets moved up and down and up and down, maybe at another instant in time, it's going to look more like this, right? And this change shows you that the displacement of a particle also will depend on the time. So it will depend on both the equilibrium position x and the time little t, right? And that is why we need this equation up here to have both x and t. And we're going to see why this works. So first of all, let's look at this x graph and look at the parts of the wave. So right here, this distance from the crest, this is called a crest and this is called a trough. And the crest is the maximum displacement, the trough is the minimum displacement. And the distance from this crest to the to zero displacement, this is going to be A. Capital A. That's going to be called our amplitude. You can see that right here. And note that this amplitude is going to be the same. Sorry, that was not a great line. I'm not a great artist, as you can see, but this A is going to be the same as this A, which is going to be the same as this A. All of these A's, all of these amplitudes are going to be the same, right? And the amplitude is not the displacement. It's just the maximum absolute value of displacement, right? So it's going to be, can sort of be thought of as negative A for the displacement, but it's still the amplitude is the absolute value. Okay, so next we can look at the wavelength of this. So I'll pick 2 points, 2 identical points, like these 2 crests. And the distance between them is lambda. And same thing with these 2 troughs. Distance, same exact lambda. And any two identical points on this graph. So you can see this point and this point, both are identical, have have the same displacement, and the displacement will go the same place, same derivative, same second derivative. They're completely identical points, or at least they should be. And the distance between them will be lambda. This point and this point are identical. The distance between them, again, lambda. Right? So lambda is the Greek letter, it's the wavelength, and you can define it as the distance between any two identical points on the x versus d graph. Right? There's going to be a different value for the d versus t graph, or the t versus d graph, however you want to say it. Okay, and that is the explanation of this graph, right? And it is going to be the equation for this is d equals a sine 2 pi x over lambda, right? That's just for this this x part. And the reason we have this 2 pi over here is if you think about it, call lambda is going to be equal to 2 pi, right? And that's for a normal sine wave. A normal sine wave will have a wavelength of 2 pi, if you remember from our video on trigonometry, right? It's going to repeat itself after 2 pi, and that would mean that this would just be a sine x, which we had already said has a wavelength of 2 pi, right? And if this lambda is 1, if you want to have, say, 1 meter of a wavelength, it's going to be 2 pi x, because after 1 meter, it's 0. It's going to be 2 pi times 0 over lambda, which is 0. Sine of 0 is 0, right? And at 2 pi, it's going to be 2 pi times 1 meter over 1 meter. That's going to be 2 pi. Sine of 2 pi is 0, right? It's going to repeat itself. And if you want to go onto a graphing calculator and see how this works, type in 2 pi x over lambda or x over L and just change L. Sometimes can't type Greek in there. I would recommend Desmos Graphing Calculator. It will let you have like a slider. And you can see why this does give a wavelength of lambda. Okay, so next we can move on this onto this graph, the d versus t graph. Okay, so I'll switch colors, right? And it's going to actually have the same amplitude. So if you think about it, the maximum displacement is the maximum displacement, right? It's not going to it's not going to vary whether you're talking about versus x or versus time. I mean, the maximum displacement of this particle is always going to be the same, whether or not you're talking about it changing with equilibrium position or changing with time, right? And that should make sense. Okay, so we now have a property called the period, right? And the period is going to be the distance between two identical points on this d versus t graph, right? So I'm going to extend this a little bit. Back to my greenish color, right? This is going to be our other crest of the wave. And this is our period, capital T, right? And this does not need to be the same as this lambda. These A's need to be the same, but the period is not necessarily equal to lambda, because lambda is like the physical difference. T is the difference in time that if you have this particle, you're saying how much time it takes for the particle to be back into its original position. And the physical wavelength of the wave definitely does not have to be equal to this period. Okay, and again, this, if you look at two troughs, I don't have a second trough drawn because I have the period very large here. But the distance between two troughs, the distance between this point and this point, distance between this point and this point, that's going to be capital T. okay? And sometimes it's useful to define another quantity, f, okay? So f is going to be the frequency. This is equal to 1 over the period. Right? And the frequency is the number of times this makes a cycle. A cycle goes through per second. So it's measured in inverse seconds or in hertz, Hz, capital H, lowercase z, which is just inverse seconds. Right? We could define something like that, but it's not super important for this x versus d graph, right? And the equation for the d versus t graph is very similar, except it's going to be, we're going to have this a sine minus 2 pi t over capital, or 2 pi lowercase t over capital T. And the minus is because we want this wave to move right with time, and you can also see if you go on to Desmos, it will let you have this t change with time. You can just type in 2 pi t over capital T, set capital T, and have this t change with time. You can just click the play on the slider thing, and you will see that the wave is going to move to the right, and if you have a plus, the wave is going to move to the left. This is the basic wave equation. I just want to go through a few other variables, okay? Sometimes it is useful, as you will see, actually, it's very useful in terms of this equation to define two other things. I'm going to call K and omega, right? And K is going to be equal to 2 pi divided by lambda. And omega is equal to 2 pi times the frequency. Pi f, which is equal to 2 pi over capital T. Okay, and you can see why this will be useful, because this is going to be d equals a sine kx fix that k, it looks a little bit like an x. Kx minus omega t. Right, and this equation is a lot easier to work with than this one. Note that this k is going to be called the wave number, and this omega is going to be called the angular frequency. Let's look at the dimensions of this, make sure these equations are all dimensionally consistent. So first, d, this is going to be measured in meters. It has the dimensions of length. Amplitude is going to have the dimension of length. It's the maximum displacement, and you can see that because it is parallel to this axis. This is a length here, right? Lambda is going to be measured in meters, right? This is a length. It's parallel to x because x is also measured in meters. Everything on this graph happens to have the dimensions of length and the units of meters. So we will use, and k is going to have the dimensions of 1 over length, and it's also going to have the units of radians per meter. I have these 2 pi's in radians. And for this time graph, we've got a that's also in meters. It's a length. D is a length. T is a time, and the period, again, is a time. And frequency will be measured in inverse seconds, 1 over time units, or the dimensions, and omega is going to be in radians per time, or radians per second. The dimensions are going to be 1 over time. Okay, one more thing I want to discuss, and that is the velocity of this wave. How fast this wave is going to move. I'm going to call that v. And v is going to be equal to lambda over capital T, right? And you should see this units of meters, second, length, time, length over time, meters per second. That's right on with the dimensions in units of velocity. That's also going to be equal to omega over k. This is the velocity of the wave, and this formula is also going to be very important.